Welcome back to our study of networks and distributed systems based on the textbook by Jim Caros and Keith Ross, Computer Networking, a Top-Down Design. We are now in Module 5, a discussion of the link layer of the TCP/IP model. We just finished the introductory section and ended that last lesson with an introduction to the network adapter, which is where the link layer is actually implemented in the system, the network adapter in each device. So let's pick up where we left off. On the sending side, the controller takes a datagram that has been created and stored in host memory by the higher layers of the protocol stack, encapsulates the datagram in a link layer frame, filling in the frame's various fields, and then transmits the frame into the communication link, following the link access protocol being used. On the receiving side, a controller receives the entire frame and extracts the network layer datagram. If the link layer performs error detection, then it is the sending controller that sets the error detection bits in the frame header. And it's the receiving controller that performs the error detection. This is a lot like the error detection techniques that we studied in the network layer. This figure on your screen shows a network adapter attached to a host bus, where it looks much like any other input-output device to the other host components. The figure also shows that while most of the link layer is implemented in hardware, part of the link layer is implemented in software that runs on the host CPU. The software components of the link layer implement higher level link layer functionality, such as assembling link layer addressing information and activating controller hardware. On the receiving side, link layer software responds to controller interrupts due to the receipt of one or more frames, handles error conditions, and passes the datagram up to the network layer. Therefore, the link layer is a combination of hardware and software, the place in the protocol stack where software meets hardware. We just noted that bit level error detection and correction, that is, detecting and correcting the corruption of bits in a link layer frame sent from one node to another physically connected neighboring node, are two of the services offered by the link layer. We saw in an earlier module on the transport layer that error detection and correction services are also offered at the transport layer as well. In this section, we will examine a few of the simplest techniques that can be used to detect and, in some cases, correct such bit errors. Figure 5.3 here illustrates the setting for our study. At the sending node, the data to be protected against bit errors is augmented with error detection and correction bits. Typically, the data to be protected includes not only the datagram passed down from the network layer for transmission across the link, but also link level addressing information, sequence numbers, and other fields in the link frame header. Both the data and the error detection and correction bits are sent to the receiving node in a link level frame. At the receiving node, a sequence of bits, that would be D in your graph there, and the error detection and correction bits is received. Note that the data and the error detection and correction bits may differ from what was originally sent because of in-transit bit flips. The receiver's challenge is to determine if the data it received is the same as the data that was originally sent. Error detection and correction techniques allow the receiver to sometimes, but not always, detect that bit errors have occurred. Even with the use of error detection bits, there may still be undetected bit errors. Therefore, the receiver might deliver a corrupted datagram to the network layer, or be unaware that the contents of a field in the frame's header have been corrupted. We want to choose an error detection scheme that keeps the probability of such a thing small. Generally, more sophisticated error detection and correction techniques incur a larger overhead. More computation is needed to compute and transmit a larger number of error detection and correction bits. Let's now examine 3 techniques for detecting errors in transmitted data: parity checks, checksumming methods, which are more typically used in the transport layer, and cyclic redundancy checks, which are more typically used in the link layer. Perhaps the simplest form of error detection is the use of a single parity bit. Suppose that the information to be sent in this figure 5.4 has a certain number of bits. We'll use the variable D to represent those bits. In an even parity scheme, the sender simply includes one additional bit and chooses its value such that the total number of ones in D plus that one bit is even. That is, the original information and the parity bit has an even number of ones. For odd parity scheme, the parity bit value is chosen such that there is an odd number of ones. Figure 5.4 illustrates an even parity scheme with the single parity bit being stored in a separate field. Receiver operation is also simple with single parity bit. The receiver need only count the number of ones in the received data plus that one parity bit. If an odd number of one-valued bits are found with an even parity scheme, the receiver knows that at least one bit error has occurred. More precisely, it knows that some odd number of bit errors have occurred. Could have been 3 bits were changed. Could have been 5 bits that were changed. But what happens if more than one bit is altered such that an even number of bit errors occurred? In other words, there were 2 bits that were changed, or 4 bits that were changed. In other words, an even number of bits arrived. It just so happened that at least some of them were the wrong bits. This would result in an undetected error. The parity check would indicate that the data was received correctly, but in fact, there were several altered bits. The truth is that if the probability of bit errors is small, and errors can be assumed to occur independently from one bit to the next, the probability of multiple bit errors in a packet would be extremely small. In this case, the single parity bit might suffice. However, experience has shown that rather than occurring independently, bit errors often are clustered together in bursts. Maybe a machine near enough to the line to cause interference malfunction and creates noise on the line, such as a power surge or a drag. Under bit error conditions, the probability of undetected errors in a frame protected by a single bit error can be much higher than acceptable. Obviously, a better error detection scheme is needed. Figure 5.5 shows a two-dimensional generalization of the single bit parity scheme. Here, the data bits in D are divided into rows and columns. A parity value is computed for each row, and another computed for each column. Now suppose that a single bit error occurs in the original bits of information. With this two-dimensional parity scheme, the parity of both the column and the row containing the flipped bits will be an error. Now the receiver can not only detect that a single bit error has occurred, but can use the evaluation of the column and row parity to identify which bit was corrupted and correct that error. Figure 5.5 shows an example in which the one valued bit in position row 2, column 2 is corrupted and switched to a 0, an error that is both detectable and correctable at the receiver. So you see, it is possible for a receiving device to actually detect and correct the bits. Although our discussion has focused on the original data bits of information, a single error in the parity bits themselves is also detectable and correctable. Two-dimensional parity can also detect, but not correct, any combination of two errors in a packet. The ability of the receiver to detect and correct errors is known as forward error correction. These techniques are commonly used in audio storage and playback devices such as audio CDs. In a network setting, forward error correction techniques can be used by themselves or in conjunction with link layer automatic repeat request techniques like those we studied earlier in the transport layer. Forward error correction techniques are valuable because they can decrease the number of sender retransmissions required. Perhaps more important, they allow for immediate correction of errors at the receiver. This avoids having to wait for the round-trip propagation delay needed for the sender to receive a negative acknowledgement and for the retransmitted packet to propagate back to the receiver, and by the way, add more traffic onto the channel. A potentially important advantage for real-time network application are links with long propagation delays, such as deep space links. Well, that's one of our schemes for detecting and correcting errors. Use of the parity bits. Before we start with the next one, why don't we take a break here, review our notes, and update everything. And when you're ready, come on back and we will examine the next example.